Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Akmal bin Abdullah from RAP 1204A with matrix number 2020619788. Today I would like to explain application of differentiation in a related rate. In a related rate problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. The procedure is to find an equation that relates the two quantities and then use the chain rule to differentiate both sides with respect to time. Okay. Then we go to first example. And for first example, air is being pumped into a spherical balloon so that its volume increases at a rate of 10 cm cube per second. So how fast is the radius of the balloons increasing when the diameter is 50 centimeter? So before we start to solve the problem, we should identifying two things from the question we given. The given information is the rate of increase of the volume of air is 100 centimeter cube per second. Then the unknown is rate of increase of the radius when the diameter is 50 centimeter. Then we express the quantity mathematically. We introduce some suggestive notation. Let V be the volume of the balloon and let R be its radius. Then the key thing to remember is that rates of change are derivative. In this problem, the volume of the radius are both functions of the time t. The rate of increase of the volume with respect to time is derivative dv over dt. The rate of increase of the radius is dr over dt. Then we can restate the given and the unknown as follows. Given dy over dt equal to 100 centimeter cube per second, then the unknown is dr over dt when r equal to 25 centimeter, because the diameter given are 50 centimeter. So for the radius we just divide into half. Then we connect the dv over dt and dr over dt. Like first we relate the v and r by the formula for the volume of a sphere. V equal to 4 over 3 pi r cube. To use the given information, we differentiate each side of the equation with respect to t. We can differentiate it using the chain rule. Dv over dt equal to dv over dr, then dr over dt equal to 4 pi r square times with dr over dt. Now we can solve for the unknown quantity. Like for dr over dt equal to 1 over 4 pi square times with dv over dt. So we substitute the r is 25, then dv over dt is 100 for in this equation we obtain. Then we got the radius of the balloon is increasing at the rate of 1 over 25 pi, which is 0.0127 centimeter per second. Then for the second example, we are given a ladder 10 feet long raised against the vertical wall. If the bottom of the ladder slide away from the wall at the rate of 1 feet per second, how fast is the top of the ladder sliding down the wall when the top of the ladder is 6 feet from the wall? Before we solve the problem, we draw a diagram and label it as a figure. Then we label the x feet be the distance from the bottom of the ladder to the wall, and the y feet the distance from the top of the ladder to the ground. And note that x and y are both function of t, which is t is time measured in second. Then we are given that dx over dt equal to 1 feet per second, and we are asked to find dy over dt when x equal to 6 feet. In this problem, the relationship between x and y is given by the Pythagorean theorem, which is x squared plus y squared equal to 100. After we know the Pythagorean theorem, then we differentiate each side with respect to t using the chain rule. So we get 2x dx over dt plus 2y dy over dt equal to 0. After that, we substitute x equal to 6, then y equal to 8. So when we substitute this value and dx over dt equal to 1, we have dy over dt equal to negative 6 over 8 in bracket 1. Then we get negative 3 over feet negative 3 over 4 feet per second. So for the top of the ladder is sliding down the wall at the rate of 3 over 4 feet per second. In fact, that dy over dt is negative means that the distance from the top of the ladder to the ground is decreasing at a rate of 3 over 4 feet per second. After that, we go to another condition, which is a water tank has the shape of an inverted circular cone with base radius 2 meter and height 4 meter. Water is being pumped into the tank of a rate of 2 meter cube per minute. Find the rate at which the water level is rising when the water is 3 meter deep. Before we solve the problem, as we know, we should sketch the cone and level it. We level the V equal to volume of water, R equal to radius of the surface, and the H equal to height of the water at the same time T, which is measured in minute. Then we are given the information that dv over dt is equal to 2 meter cube per minute, and we are asked to find dh over dt when 3 is depth of the water, r 3 meter. Then we relate the v and h into the equation of cone, which is v equal to 1 over 3 pi r square times h. Then we eliminate r using the similar triangle of the figure to write r equal over h equal to 2 over 4, which is r equal to h over 2. Then we express the v into the formula. Then we got v equal to 1 over 3 pi in bracket h over 2 close the bracket power of 2. Then we got h equal to pi over 1 over pi over 12 h cube. Now we can differentiate each side with respect to t. Then we got dv over dt equal to pi over 4 h square dh over dt. So dh over dt we get 4 over pi h square dv over dt. Then we substitute h, which is h is 3 meter and dv over dt is 2 meter cube per minute. Then we got the dh over dt is equal to 4 over pi times with 3 power of 3 times with 2. Then we get the 8 over 9 pi. The water level is rising at the rate of 8 over 9 pi, which is 0.28 meter per minute. So thank you.
For the first problem, this is the problem statement. The closed cubeboard has a square base and its height is triple its base. If x is the length of the base and x is increased at the rates 4 cm per second, find the rates of change of the surface area when x is 8 cm. For this statement, we can get the information that dx over dt is equal positive 4. The sign is positive because it is increasing. If it is decreasing, the sign will be negative. From the statement, we also know that the height of the cubeboard is 3x because it is triple the base length is x. The problem wants us to find the rates of change of the surface area when x is 8 cm. So we can write dA over dt equal unknown when x equal 8. To find dA over dt, we need dA over dx to multiply with dx over dt. Next, we need to find the area of the cubeboard. 2x squared is the area for the top and the bottom of the cubeboard, while 3x squared times 4 is the area for the side of the cubeboard. The total area of the cubeboard is equal 14x squared. Now we need to differentiate. So dA over dx equal 28x. Now we bring this back here and replace dA over dx and dx over dt. The question asks us when x equal to 8. So we need to replace x with 8. And the final answer is 896 cm squared per second.